Okay, we begin part 2. We mentioned this result of Leibniz for part 1 because it is used in another great theorem, actually, which is due to Bernoulli brothers. So our next characters are Jacob Bernoulli and Johann Bernoulli. So it was Jacob, actually. They both are contemporaries of Leibniz. Jacob Bernoulli is known for establishing the basis of modern probability theory as we know it today. And both Bernoulli brothers actually made enormous contributions to calculus, much in the form that it is studied and used today. But we shall talk about a great theorem of Bernoulli's brother. Well, Jacob Bernoulli worked on it first and he couldn't solve it, let's say, and it was Johann Bernoulli that actually gave a first proof of this theorem that I'm going to just write in a little bit. And then his brother Jacob gave a different proof of the very same theorem, but probably it is a bit much for this particular book. So we shall just discuss the very first proof given by Johann Bernoulli. Okay, so the statement again has to do with determine a particular sum of infinite series, and that would be the harmonic series. So here's the theorem. They proved, or Johann Bernoulli proved first, that the harmonic series, a harmonic series is actually a series, well, an infinite sum of all the reciprocals of natural numbers. So natural numbers are 1, 2, 3, 4, 5, and so on. So their reciprocals would be 1 over 2, 1 over 3, 1 over 4, and so on. And harmonic series is called the infinite sum of such reciprocals. So the harmonic series 1 plus 1 over 2 plus 1 over 3, 1 over 4 plus, okay, 1 over 5 plus 1 over k plus plus is divergent. That means that this infinite sum does not sum to anything in particular, does not sum to a finite number. That's why we say it is actually divergent. So, proof. I will move back to this side so I can use this space. Okay, so the sum of the series that we want to determine is the harmonic series. So let A be called this harmonic series. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over k plus plus and so on. So we're calling what we want to find out, whether it diverges or converges, we're calling that A. Okay? And let C, that's another sum, be the sum, well, let that be the telescoping sum from Leibniz. So I'm going to call C the telescoping sum that we just talked about in part 1. So half plus 1 over 6 plus 1 over 12, 1 over 20, plus 1 over 30, plus so on. We know from part A that C is actually equal to 1. That is the telescoping series. Okay. And also I'm going to call D the following sum. I'm going to call D a sum that looks almost identical to the telescoping series, but removing that first term. So if I remove the first term, whatever is left is this sum, 1 over 6, 1 over 12, 1 over 20, and so on. I'm calling that D. So 1 over 6 plus 1 over 12 plus 1 over 20 plus 1 over 30 plus and so on. Well, what is D possibly equal to? Let's see if I can actually determine the sum, if it actually sums to anything. Well, this would be equal to what? That would be equal to half. That is actually equal to 1 minus half. Why? Because is nothing other than the telescoping series from above minus that first term half. I know that the telescoping series from before, so the entire telescoping series is 1, but D is everything in telescoping series minus the first term, so that would be actually equal to half. So D is equal to half. Let me call E, almost identical series just as D, but removing that first term. So it's exactly D, but removing 1 over 6. So E will call 1 over 12, 1 over 20, 1 over 30, plus and so on. So E is nothing other than D, whatever this D sums up to, minus that very first term, which is the 1 over 6 term. So E is equal to D minus the first term, which is 1 over 6, or half minus 1 over 6. Half minus 1 over 6 is equal to 1/3. And let F be exactly the same as E, but removing that first term, 1 over 20 plus 1 over 30 plus so on. That would be the same as E, whatever E was, minus the very first term, which is 1 over 12 here, and we'll have that to be 1/3 minus 1 over 12 equals to 1 over 4. Okay, and well, for the sake of completeness, let's just write G. G is the same as E, but removing 1 over 20, so is 1 over 30 plus whatever the other terms are, and that is the same as F minus the first term of F, which is 1 over 20, and that is the same as 1 over 4 minus 1 over 20, or equal to 1 over 5, and so on. So here is and continue doing this. Now, if we continue doing this, we are going to do the following. We are going to add the two leftmost columns, to actually get C. Forget about A. I'm not adding A to this, but let me just add those. So adding those, it means I'm going to add whatever they sum up to. So let's see. All right, well, let's see. So let me write that. Now we add the two leftmost columns. So what would they be? This is one leftmost column. The other one would be what? It would be right, let's see. would be this and this and this and this and that. So so we add C plus D plus E plus F plus G plus and so on. Okay. Well, let's see. That would be equal to 1 over 2 plus 1 over 6 plus 1 over 6 plus 1 over 12 plus 1 over 12 plus 1 over 12. Here's what we're doing. This plus this 2 plus this 3 plus this 4 plus this 5 and so on, plus 1 over 20 plus 1 over 20, 1, 2, 3, 4, plus 1 over 20 plus 1 over 20, and then 1 over 30 and so on. Okay, so adding this, then this, plus this 2, plus this 3, plus this 4, plus this 5, and so on. All right, and let's see what we get. So 1/2 plus 1 over 6 plus 1 over 6, that would be plus 2 over 6, plus 3 over 12, plus 4 over 20, and so on. But 2 over 6 is the same as 1 over 3. 3 over 12 is the same as 1 over 4. 4 over 20 is the same as 1 over 5, and so on. So the sum of C plus D plus E plus F plus G plus all of that equals exactly my sum that I'm looking to determine, sum A. So this is equal to the sum A. So on the other hand, maybe I should start another page. Equals A. All right, lecture 11. 11. This is page 3, and part 2 continues. Part 2 continues. Okay, so on the other hand, adding the leftmost and the rightmost columns, that means adding the leftmost and the rightmost columns, we'll get what? We'll get the following. I repeat, we are going to add the leftmost column now and the rightmost column. That is 1 plus half plus 1/3 plus 1/4 plus 1/5 and so on. C plus D plus E plus F plus G and so on. Okay, so on the other hand, adding the leftmost and the rightmost columns we get what? We get the following. C plus D plus E plus F plus G plus so on. Let me show you. I'm adding this and I'm adding this as well. That's what we mean by the rightmost column. So here I have 1 plus half plus 1/3, 1/4, 1/5 and so on. Let me just write that. So it is equal to 1 plus half plus 1/3 plus 1/4 plus so on. But we just determined from the previous page that this left hand side is equal to a, and this other right hand side turns out to be 1 plus a, because 1 plus 2 plus 1 over 2, 1 over 3, 1 over 4, and so on is the harmonic series that we're looking to determine. So we get to this statement. We're saying that could A possibly be equal to 1 plus A? Is this something that can happen? Well, let's see. Is it possible? No finite quality, or not quality, no finite quantity is actually equal to 1 more than itself. So this is an impossibility. It's a contradiction. Therefore, the harmonic series cannot possibly sum up to a finite number, meaning it is divergent. So I'm just going to write that. No finite quantity is equal to 1 more than itself. That could only mean that A is an infinite quantity. Is an infinite quantity. With other words, the series is divergent. Okay, so that will constitute the proof of this little gem from Bernoulli brothers, and that would be the end of part 2. I'll continue shortly with part 3.